Well, I would just want you to have an idea because I'm going to do a full example now using the definition so you can see how we used to do this more than 100 years ago, maybe 200 years, okay? 200 years ago, but then of course calculus started to be developed, and then we have more clever ways to actually compute area, and that's what we're going to focus on. So do not stress too much on this first part. When I say not stress, it's because I'm not going to test you on the definition of this, on what I'm about to do. However, you need that knowledge to be able to understand what you're going to do in calculus 2. When you start talking about volumes and other things, you will need this point of view, okay? So it's good that you look at it. Otherwise, you're going to be lost later on. Anyways, and so you see also that, you know, what we are actually doing here makes sense. Okay, so here's the question. Find the area of the plane region bounded by the graph of this function, negative x squared plus 5, the x-axis, and these two lines, x equals 0, x equals 2. Remember, those are vertical lines. So let's just draw a picture to understand what this is. Okay, so that's a parabola. That's a face down and shifted up 5 units. Let's say 1, 2, 3, 4, 5. So here's the vertex. Then it opens down, but I'm only interested from 0 to 2. So just let me just draw the whole thing. Something like this. Let's see the what are the x-intercept? We said equal to 0. That's square root of 5. Plus or minus square root of 5. So let's say this is a 1, this is a 2, so somewhere in here. But I care about from 0 to 2. So if I plug in 2, I get 1. So I guess. You know, something like this. So this is the function f. This is y equal f of x, and then the question is, we want to find this area right here. Okay, all of this. Because we have the function, we have the x-axis, then we have the line equals 0, and then if you want, here we have the line y equals 2, x equals 2. Okay, so the region in the plane bounded by the function, this line on the x-axis is the one that's shaped. So you understand this? Including this little piece, not just this, but this part here as well. Does that make sense? Okay, so I want to find this area. So the question is, okay, how do we do this? How do we find the area? So, you know, this is not a formula that we know. I mean, this is not a shape that we have a nice little formula that you can compute, like base times height or that kind of stuff, like a rectangle or a triangle, etc. So what is the idea? Well, the idea is that if you want to compute this area, what we can do is we can approximate the area with shapes that we know, okay? And the basic, one of the most basic shapes are rectangles. So the idea is, let me just do a quick, just do a couple of scenarios here. So we have here 2, so let's say this is a 1. What you could do is, for example, okay, I'm going to use 2 rectangles, okay? So let's say rectangle of base 1, and then, I don't know, I'm going to use the right endpoint, okay, for the height of the rectangle. So here's one rectangle. And then similarly, the other one, I'm going to use the right endpoint. Actually, I'll be up to here. Here is my other rectangle. Okay, and then I know how to find, by the way, you know how to find the area of this rectangle. The base is 1, and the height is whatever the value is at 1, right, of the function. Same thing for this one. The base is 1, and the value is, the height is whatever value the function has at 2. If you add these two areas, this is not exactly the answer, but this would be an approximation, okay? Why approximation? Well, this is an underestimate because notice that there is a bunch of little pieces that we're missing. The idea is that instead of 2 now, use 4, we improve this approximation a little bit more, okay? So for example, if I use 4, and notice that if I use 4 rectangles instead of just 2, how would the picture look like? Again, we have the same interval, 0 to 2, okay? So it equals 1 here, okay? We have the same interval from 0 to 2, but now I want to stick 4 rectangles instead of 2, and I want the base of my rectangles, if you notice, to be always the same, okay? So I want that to be the same, so I have to split this into 4 pieces, right? So this is now 1, but this guy is 1/2, and this guy is 3/2. Yes? I repeat the same idea. Here I'm using the right endpoint. But for example, if you use the left endpoint to decide the height, that would be an overestimate. Do you understand this? For example, this is called a lower sum. If you do it with the right endpoint, that's an overestimate. That's called an oversum in this language. But don't worry about that for now. Just do this, then the next one, the next one, and the next one. So, and we calculate the area of these rectangles, which, by the way, we know how to compute this. The base of the rectangles is 1/2, right? And the height is, the first one is the value of the function of 1/2. Just plug in, you get the height, then a 1, and so on. So notice now that by using 4 rectangles, again, it's an underestimate because, we are not covering the whole thing. But now the stuff that we're missing is less than what we were missing before. Do you understand this? What do you think is going to happen if we use 8 rectangles instead of 4? So we're going to be missing less. Still missing, but less. So what's the idea? We want to use as much as we can. Okay? So we're going to define this area to when we do this process, but then instead of just using 4, 5, 6, 20, 100, we're going to use infinitely many rectangles. Okay? Now, how do we talk about infinitely many? Of course, we're going to say we're going to have a bunch of rectangles, let's say n of them, and then we're going to take the limit as n approaches infinity. Okay? That's the idea. That's how we compute this. Now, the point is that this limit approach is, it's really not straightforward. We're going to do this example with the limit approach, but if the function is a little bit more complicated, then it gets out of hand. That's why we need more techniques. Just like when we're talking about derivative. If you want to do derivative using the limit definition, you could do it, but if I give you a complicated formula, it's going to be there forever. Okay? And then we develop some rules to be able to find derivative. Anyways, so that's the idea. We're just going to approximate using rectangles. I'm going to compute the area of these rectangles, and then we take the limit. Does that make sense? All right. So I guess the remark here is we may approximate, let's call this area A. So we may approximate the area using rectangles. For example, in here, the lower sum, I'm going to call the lower sum because I know lower and underestimate, I'm going to call it little s. Okay? So then little s, in this case, what is this equal to? That's going to be equal to the area of the first rectangle. Then let's call this R1. This one will be R2. So it will be the area of the first rectangle plus the area of the second rectangle. Yes? So what is this? What's the area of the first rectangle? That's 1 times the value of the function of 1 plus 1 times the value of the function of 2. Base times height. The base is 1 and the height is the value of the function of 1. Yes? The second rectangle, the base is 1 and the height is the value of the function of 2. And we know that, in this case, this is less than or equal than the area. In fact, it's less than, okay? Now, we keep on doing the same thing. We call this typically S2 because we're using 2 rectangles. Now, if instead of 2, we use 4 rectangles, what would this be? What's the area of the first rectangle? Who can tell me?
Half times the 1/2.
1/2 times the height, which is the value of the function of 1/2. Yes? Plus 1/2 times the value of the function of 1 plus 1/2 times the value of the function of 3/2 plus 1/2 times the value of the function of 2. Okay? And by the way, notice that we can just factor out the 1/2, and what we really have here is the sum. Okay? Because the base is the same, so you just factor it out. So this is going to give you a number, and once again, this is an underestimate of our area, but the more rectangles we take, the better will be approximation. The idea here is, well, just compute Sn, you call it little s. So using n rectangles, right? And then, if you want to compute the actual area, let's look infinitely many. And this is how we're going to define the area. Okay? So this area, we're going to compute it as the limit as n approaches infinity of this little sum. In other words, The meaning here is that we're taking infinitely many rectangles. Do you understand what I'm saying? Okay. Now the question is, how do we get this formula? Well, it varies from problem to problem depending on the function. In this case, we'll be able to do it, but we have to borrow some formula from pre-calculus. Okay. But if this is a trigonometric function or something more complicated, then it goes out of hand to do it this way. That's why Fundamental Theorem of Calculus is so nice, because it allows you to compute this very nicely if you know how to play the game of antiderivatives. Okay? So we're going to do that later. But right now, let's understand this. I just want to give you an idea how this is done. By the way, this is a big sum. Here we're adding n rectangles, okay? We're adding n numbers. So we need to have a nice notation, because as you can see, here I only have 4, and this is already very painful to write. Imagine that if I had 20 rectangles. I don't want to sit down there and write a sum with 20 things, okay? So we have a way to write this. So sigma notation, sigma or summation notation. We say sigma because we're going to use the capital letter S in Greek, which is called sigma. You know Greek, right? Okay. So sigma notation, and we're going to use this symbol, or yeah, it looks like that, and this is capital letter S in Greek. Okay, S for sum. Okay, because we're going to be adding things. And basically, for example, imagine that you want to do 1 plus 2 plus 3 all the way up to 20. How do you write something like this? How do you write this in a shorthand way? Well, if you know a little bit about programming, what we can do is we can put like a counter. Okay, we can designate a variable that's going to take place. It will be 1, then it's going to be 2, then it's going to be 3, and so on, all the way up to 20. So this is a variable that's going to go from 1 to 20, and then we want to say somehow that we want to add those numbers. So this is what we do. So we put this. This means I'm going to be adding something. So we put I or N, whatever is your favorite letter. This is a variable, and this I takes on these values, either 1, 2, 3, or whatever. And the way to say that is we say, okay, it's going to begin at 1, and it's going to stop at 20. So if you look at this notation, what I'm saying is I'm going to be adding all the numbers from 1 all the way up to 20. Do you understand this? Yes? For example, how do you write this? How do you write this?
I squared.
Very good. So it's the same thing. Now this time is from 1 to n. And you do I squared. Okay? And then, I guess. And the example that we had above, let's see if instead of 20, let me just reuse this one. If I put an n in there, meaning I want to add n numbers, the first n numbers, then you just put an n in here. Okay? And so on. Now, there are formulas for these things. Okay? You study that in pre-calculus, for example. Here, there's a nice little formula. This is due to Gauss. He did it when he was 8 years old, by the way. He was a genius. But anyway, we have a formula that you can use to add consecutive numbers, integers. And it's going to be n times n plus 1 over 2. For example, let's say that you want to add the first 5 numbers, 1 plus 2 plus 3 plus 4 plus 5. What is that equal to? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. Yes? Well, what Gauss said is, well, all you have to do is 5 times 6 over 2. Now you say, well, why do you want to do that? Well, what if you need to add from 1 to 100? You don't really want to sit there and do 1 plus 2 plus 3, etc. But now we can do it. It's 100 times 101 over 2. Okay? And so on. We're going to need this, by the way. So we have that formula, and then there's also one from the square, for the square. That one is a little bit more involved. Let's see. We have that. Square. Okay. So that one is n times n plus 1 times 2n plus 1 over 6. And there's one for the cubes, which is, that one is easy to remember because that one is the square of the first one. Okay? So if you add consecutive cubes, that's going to be n squared times n plus 1 squared over 4. Okay? All right. And again, you may wonder, well, how can one come up with something like this? Well, you start doing experiments. Like, you ask yourself this question, then you start observing, do what happens when n is equal to 1, then when n is equal to 2, n is equal to 3, and try to observe the results and see if you can make a conjecture, like I don't come up with a formula. If you somehow can see this relationship, then the question is, okay, is this always true? And then there's a technique called induction, mathematical induction. You learn in discrete math, this for example, that would allow you to realize whether this is true for every n. Okay? But anyways, we're taking this for granted now. I'm putting this because we're gonna need these two formulas. All right. Also, for example, let's say in this case, I'm gonna be adding areas. So the area of n rectangles. Okay. How do we write this nicely? You know, this same notation, this is very dynamic. You can use it whatever you want. You can write this nicely as the sum from 1 to n, because I have n quantities here, of a ri, right? Because the little thing that's changing is this subscript down here. Do you understand this? So I'm going to be using those symbols, but understand that this just means a sum, okay? All right. Questions? Okay, so now let's go back to our problem. So I want to make sure that I have an expression of Sn, so then I can take the limit, and that will be my area, okay? So let's try it. So to find Sn, you know, by definition, this is Sn, right? It's the sum of the areas of the n rectangles. Everybody okay with this? So to find the area of the rectangle, I need the base and I need the height. So we need base and height. Now we know exactly how to do this. So for example, in the case of 2 or 4, how do we find the base? What do we do? If you wanted 2 rectangles, you divide the interval from 0 to 2, which is the one that you care about, into 2 pieces, right? And you know the base is going to be half, 1 and 1. If you wanted 4 rectangles, how many pieces do you divide? How many pieces? 4 pieces. So if you want n rectangles, how many pieces do we need to divide this? In n pieces. Okay, so that's the first thing that we need to do. So for the base, we want to split the interval 0, 2 into n. It doesn't have to, but it works if we do it in equal pieces, and it's easier for computations. Okay. In general, this is called a partition of the interval. We're going to split this into n equal pieces. Partitioning means just split it into pieces. They don't have to be equal, but they have to satisfy the condition that it's a formula that when n increases, the size of the partition decreases. Okay, so the little pieces, they decrease all with each other. So the easiest thing is just to do it equal. So that means that here I have 0, I have 2, so I'm going to do 1, 2, 3. Here is a generic piece, and so on. So for example, I'm going to call this one x0, I'm going to call this one x1, x2, x3. At some point, it's going to be xi minus 1. This is xi, xn minus 1, and xn. Okay? Notice that I need to have n plus 1 numbers, because here we have 4 pieces, but we have 0. There is 0 here. So 0, 1 half, 1, 3 half, and 2. That's 1, 2, 3, 4, 5. So this is my x0, my x1, my x2, my x3, my x4. Okay? It's just a notation, what I'm using now. And our job is that we want a formula for these guys. Okay? We're going to get to that. First of all, let's figure out how much is this. What is this length? Which, by the way, is the same for everybody. Yes? So what is that length? What would that be equal to? In the case of 4, it was a half, right? How do we get a half? In other words, if I give you something and I ask you to split it into 7 equal pieces, what do you need to do? Yeah. What's the length of each piece? What will be the length of each piece? Say that again? So divide by 7, right? You take the length and divide it by 7. Okay. What's the length of this interval? 2. So what's the length of each piece? 2 over n. Does everybody understand this? So the length here is 2, which is, but in general, how do we compute it? And right, for example, this would have been, let's say, from 3 to 7. What would be the length? 4, right? Which is 7 minus 3. Everyone understand this? So in general, we do right endpoint minus left endpoint. So 2 minus 0, and then divided by the number of intervals that you want. If n is equal to 4, if you want 4 rectangles, that's 2 over 4, which is a half. If n is equal to 2, that's a 1, right? And so on. Okay, so this little piece, so, okay, let me say here, the length is 2. So this little piece is going to be 2 over n, okay? And understand that this is 2 minus 0 over n, because later what we're going to do is instead of a 0 and a 2, we're going to have an a and a b in here, okay? So the formula would be b minus a divided by n, okay? All right, so let's take a generic interval because everybody is the same. On one hand, this is equal, of course, left minus right, yes? And on the other hand, we know this is 2 over n. So let's use this relation to come up with a formula for these guys. Because if you start here, since you already know how long this has to be, all you need to do is do this one plus 2 over n to get x1, plus 2 over n to get x2. And you keep on doing this till you get the last, right? So I want to know how much is this, the formula for this guy is what I want to know, okay? Okay, so we have that, let's see, let's do it. So x0 is equal to 0, okay? Then x1 is x0 plus 2 over n. By the way, we have a notation for this. We typically call this delta x, okay? It's changing x, a little changing x. So we use delta x for this. So that's, use the notation here. That's x0 plus delta x, okay? Now, how do we compute x2? What's x2?
x1 plus delta x.
Would be x1 plus delta x. Just keep on adding 2 over n, okay? But then remember, what is x1? x0 plus delta x. So this is going to be x0 plus 2 delta x. Do you understand this? So if we actually put what our delta x was, actually, since I'm here now, let's just put everything. Because x0 is 0, right? Okay? So if we keep on doing this, what's going to be the I element in here? What's xi? What will be a formula? Look at the pattern. x1, there is a 1 here. x2, there is a 2 here. So what should be xi?
xi minus 1 plus delta x.
And what will be a formula for that? x0 plus I times delta x. Yes? I mean, just keep on doing this. Let's see, let me do one more. What's x3? x2 plus delta x, but what was x2? x0 plus 2 delta x, right? You are just adding delta x, so that's x0 plus 3 delta x, right? With the pattern, 2, this is 2 here, 3, this is 3 here. So if we keep on going, what's xi?
x0
plus I times delta x. Yes? All right? So notice that this was 0 plus 3 times 2 over n. Because our delta x is 2 over n. So that would be 6 over n. Okay? And then finally, by the way, I guess, let me keep it like this. 2 times 2. Then 3 times 2. Notice that there is a 2 here. Here is a 3, and here is a 3. So this would be 0 plus I times 2 over n. So the formula is 2i over n. Okay? So again, it's consistent, right? So we have an I is 2 times I. We have a 3, 2 times 3, 3 times 2, whatever you want. And let's just make sure that this formula makes sense. So when I is equal to n, what am I supposed to get as a result? Don't look at the formula. What am I supposed to get as a result when I is equal to n?
2.
We're supposed to be at the end of this line, so we better get 2. Okay? That's how you can test to see if your formula makes sense. Let's see. If I is equal to n, according to the formula, that's going to be 2 times n over n. And what is this? That's a 2, so we're good. Okay? So moral of the story. xi equals 2i over n. We're going to need this. Okay? Okay, so for example, you can think of this then as being 0. Then what's the next one? 2 over n. What's the next one? 4 over n. Then, so that's I equals 0, I equals 1, I equals 2, I equals 3. This is 6 over n. Keep going. 2i minus 1 over n. 2i over n. Keep going. And then the last one is going to be 2 times n minus 1 over n, and then the 2 here. Okay? This is how partition is looking. So now that means that we know the base of our rectangles, right? And then we just need to figure out the height. So base is delta x, which is always 2 over n. That's our base. It's 2 minus 0 over n. Okay? And what's the height of the rectangle? Well, at this point, it depends. Okay? In our case, for example, in these problems, in this example that I was doing, I was using the right endpoint to find the height of my rectangle. But you could use the left endpoint, or you could use the middle point. In fact, you can use whichever you want in between. But you need a formula for that. We already found a formula for this guy, so at this point, we use the left endpoint or the right endpoint. Just to be consistent with these pictures that I have here, I'm going to keep on using the right endpoint for the height of my rectangles. Okay? Remember, what's going to change is that you either get an overestimate or an underestimate for a fixed n. Okay? Or something in between. For example, if you use the middle point, what's going to happen is that you're going to have a piece inside, but then another piece that goes outside the figure. Then inside, outside, they kind of compensate with each other. Okay? But still, it will be an approximation. So I'm going to use the right endpoint just to. So using the right endpoints, first I'm going to write it in the long way. Okay? Then the area, then little Sn, remember is the sum is AR1, the area of the first rectangle plus the area of the second rectangle, and so on, all the way up to the nth rectangle. I'm gonna write the long thing. So now area of a rectangle, base times height. What's the base? It's delta x. What's the height? The value of the function at the right endpoint. So the right endpoint here, let me look at the x's. So for the first rectangle, the right endpoint is x1. Do you understand this? For the second rectangle, the right endpoint is x2. Yes? So it's going to be delta x times f of x1. That's the area of the first rectangle. Plus base times height. That's the area of the second rectangle. All the way up to the area of the last rectangle. If we were using the left endpoint, then you will stop. This will start at 0 and you stop at n minus 1 because it's the right endpoint. Like for example, the last rectangle here, which is this one, the height is given by this guy, not this one. Okay, so you will stop here. But because I'm using the right, then I'm going. I don't use 0. I use this one, and then I stop here. Okay. So now let's put in our formulas. So this is the same thing as saying I'm gonna now use the nice summation formula. By the way, well, let me just keep it like this. This is the sum from 1 to n. Notice that what's changing here in this expression is the subscripts of the x's. Yes? So that would be f of xi times delta x. Right? Then nothing else is changing. The only thing that changes is the stuff inside the f. And we have a formula for this. That's why we need it. What's the formula of xi? Is 2i over n. Okay? So this is going to be equal to the sum from 1 to n of f of 2i over n times delta x. But what's delta x equal to? 2 over n. You okay with this? Just plug in what we have. So this right here is a formula now for Sn. And what we want is to take the limit. Now, this limit is not good because we have an n here. So you will say, well, what does it mean to have an infinity here? That's something you will start in calculus 2. So the question is, can we write this in another way? Okay, can we write this in a more comfortable way for us to take the limit? Because that's what we want to do. So I'm going to keep on working with this. At this point now, I'm going to use the function. What I just did now is general for any function. You can do it for any function. Okay? And instead of being from 0 to 2, if you do it from a to b, the interval, what changes is that this top here will be the b minus a, right? The length of the interval. And then this is going to change accordingly, of course. Okay? Because instead of starting at 0, you start at a. So this logic here, this formula is the one that never changes. But if you start at a instead of at 0, it will be a plus I times delta x. So a plus I times delta x. Okay, will be the formula. But it's the same idea. Okay, so this is my function. So now let's plug in and let's do some algebra. So this is the sum from 1 to n of negative 2i over n squared plus 5, and that gets multiplied by 2 over n. So this, okay, so remember, what is this? This is just a big sum, right? It's this sum right here. What you could have done before I wrote this down, we could have factored the delta x. Yes? That means that in this summation, this delta x will be outside, multiplying the entire sum. So in other words, when you have a finite sum like this, you can take constants out. That means factor. That just means factor. Okay? So take a constant out means to factor. So I'm gonna take out 2 over n. Okay, and then this will be minus 4i squared over n squared plus 5. I just did this square right here. Another thing is distributive property. So if I have this, let's see, if I have x1 plus y1 plus x2 plus y2, I'm just gonna do it with 2, but I can have as many as I want here. I can do this, or I can rearrange things, right? I could do x1 plus x2, and then plus y1 plus y2, and then combine. Do you understand this? Right? So I can do that. Well, that's exactly what we can do here, because if you think of this as being a summation, this would be the sum of xi plus yi, from 1 to 2 in this case. And basically, and the other part says the sum of the xi's plus the sum of the yi's. In other words, if you have a summation, just like when you do with derivative and integrals, if you have a summation and you are adding stuff inside, you can break this into two summations, as long as it's a finite sum. That just means that you are regrouping. You're grouping things together and then split. Okay? That's just the grouping property. So here, I can write this as two summations. Okay? I'll leave that one there. Basically, the property is you have the sum from 1 to n of ai plus bi. This is the sum of the ai plus the sum of the bi's. So you can add the a's together, you can add the b together, and then add the results. Okay? Instead of doing mix 1 on 1 on 1 on 1. Okay? That's exactly what's happening. So that's what I'm gonna do there. So I have my 2 over n, and then I have two summations. Again, the reason why I'm doing this is so that hopefully you will appreciate them later. The fundamental theorem of calculus, because it allows you to bypass all of this. And this problem will be able to do it in one little line. But before fundamental theorem of calculus was around, this is what people would do. Okay, so you split this as two sums. Now, for example, this one, who can tell me what is this? What's the meaning of this one?
5 times n.
Very good. This just means you're going to add repeatedly 5 n times. You see, there's no I here, so that just means you can think of this as a counter. Okay? For example, if you're into programming and so on, think of this as a for loop. And this is just telling you from 1 to n, do this. Do what? Add 5. 5 plus 5 plus 5 plus 5, n times. So just n times 5, or 5 times n. Does that make sense? Okay. So, okay, that one is easy. So this part here is a 5n. And then this one, well, negative 4 over n squared, that's a constant, so I can take it out of the sum. Remember, the variable here is I. This is the thing that's changing from 1 to n. That's the one that we cannot just take out, but the rest we can. Okay? And then we come here, and what is this? This is the sum of consecutive perfect squares. 1 squared plus 2 squared plus 3 squared, etc. And as I mentioned before, we have a formula for that. When you add consecutive perfect squares, that equals the last guy times the last guy plus 1 times 2 times the last guy plus 1 divided by 6. Okay? Just going to use that one. So that's n times n plus 1 times 2n plus 1. So negative 4 over n squared times, now this is n times n plus 1 times 2n plus 1 over 6. And this is our Sn. And even though you may say, oh, why do you want to do something that looks so complicated? Well, this is not something that we can take the limit of. If you take the limit of n approaches infinity, what you have here is a rational expression. I'm going to simplify it now, but this is a rational expression. We know exactly how to take this limit. Okay? So let's make this nicer now. Now these are just cosmetic adjustments. Okay? So for example, I can simplify this n over here, and then if you want this 4, that's a 2, and this one is a 3. So now this is 2 over n times. So let's see, I'm gonna get negative 2 times n plus 1 times 2n plus 1. Okay, so that's 2n plus 1 over, so what is this, 3n? Okay, and then I distribute, and this is gonna be negative 4 times n plus 1 times 2n plus 1 over 3n squared plus 10. Because the 2 over n times 5n, the n's cancel and you get 10. Everybody okay? Now, I'm not going to combine this because as long as you can take the limit, that's fine. We can take the limit of this. So, the area that we're looking for is the limit as n approaches infinity of this expression, which, by the way, let me write it formally. This is the sum from 1 to n of f of xi times delta x. Okay? This is what I want you to remember. This is the definition. And delta x here, let me just do it completely, where delta x is 2 minus 0 over n. But I want you to think of this as b minus a over n, in which a is 0 and b is 2. Okay? Because that's how we're going to look at it later. And xi happens just to be the right point, as we just saw before. So for example, xi, our formula was x0 plus I times delta x. That was the formula we came up with. Okay, but that's fine. We already have an expression for that. So it would be the limit as n approaches infinity of this quantity. Okay, and what is this equal to? Number here. So let's see, that one where there's a constant, that's 10. So as long as this limit is a number, then you know the result here is going to be the sum of the two numbers, right? So what is this limit equal to? This is a rational expression, a limit at infinity. How do we compute it? You look at degrees, right? That's the fast way. What is the degree of the top? 2. Degree of the bottom? 2. So the limit is going to be ratio of leading coefficients. So what's the leading coefficient of the top? Negative 8. Everybody see that? So you get a 2n squared from here, but then distribute the negative 4. So that's negative 8, and the bottom? 3. So the answer here is going to be negative a over 3 plus 10. Okay? By the way, are we expecting a positive or a negative number? A positive, because look, we're looking for area, and this is above the x-axis. So area is positive. Okay? Okay. So now what is this? That's going to be 30. So 30 minus a is 22. Okay? So that's the exact area, 22 over 3. Again, I'm not going to ask you to replicate what I just did. This is just for you to understand what this means. When you write this down, well, now we're going to have a way. By the way, let me just say, note. We write, in this case, a, we write it as this. We're going to use the integral symbol, and we write it as the integral from 0 to 2 of the function f. But right now, when you write this down, a priori, this has nothing to do with what we have been talking about. If you didn't have the 0 and the 2, that's an indefinite integral. Later, you're going to see, today, you're going to see why we're using this symbol. But this right now, what it means for us is this. This is the limit as n approaches infinity of a sum. What sum? The sum of the areas of the rectangle. This is called a Riemann sum. Okay? F of xi times delta x. That's what it means for us. Okay? That's what this means for us. In this case, we were successfully able to compute it, and it happens to be 22/3. Okay? Now, we're going to learn that we can actually come up with this number in one line instead of having to go through all this. But this is what used to be done back in the day. But you need to understand the meaning of this and this idea of approximating the area with rectangles and so on, because in Cal 2, when you talk about volumes, you're going to be doing a similar process. And then you cannot just get away by solving an integral. You have to be able to set up the integral. Here, the integral is very straightforward. We integrate a function. I'm calling this integral because it's called a definite integral. I just put the function and then you do whatever you need to do once you learn fundamental theorem of calculus. It's super easy. But how do you compute volume? That's a different story. You have to figure out what expression you need to integrate. And for that, you need to understand how the approximation is done. Okay? So if you don't, it's good to have a feeling about this, an idea of this, because this idea will be expanded later on for further applications. Okay? That's why I think it's valuable for you to see this. All right. Anyways, do you have a general idea of what I just did? Bunch of rectangles. Just try to fight to come up with a formula for the area of these rectangles. You add them together, take the limit. Okay? So this is what we call a definite integral. So let me define that. So definite integral. So I'm going to kind of summarize all the story that I just told you. Okay? In what you will see here. Now, there are some conditions that we need. For example, you have to make sure that this limit exists. Because what if you're taking a limit? What if it doesn't exist? Now, a condition that guarantees the existence of this limit is if the function is continuous. If you have a continuous function, you can always play this game. Okay? So that's why we begin with this. In general, we need the function to be integrable. And the theorem is that if the function is continuous, then it is integral. Okay, so let f be a continuous function on the closed interval AB. Now I'm going to generalize what we did before, okay? And then suppose that we have a partition. You know, these are my x0, x1, all the way up to xn. So this is a partition of the interval AB. So what this means is that, you know, x0 is equal to A, and then comes x1, then comes x2, in increasing order, and then finally we have xn, which is B. Okay? That's what a partition is. So let me draw the picture here. Here is A, here is B. So, you know, basically, and then, you know, we're going, what is it that we do? We split this into n pieces. Same idea. And this is my x0. Here is my x1, my x2, x3, all the way up to xn minus 1. And then the last guy is xn. And then we always like to take a generic interval, like the ith interval. Okay? Which would be, so the first interval is from 0 to 1. The second interval is from 1 to 2, and so on. Okay? So xi minus 1, xi. So that's a partition that we have of intervals xi minus 1, comma xi. Now, what's the length of this interval? Well, this length, remember, we call it delta x, and, you know, the naive thing to do is to subtract, right? Right endpoint minus left endpoint. But we also have a formula for this. How can we figure out this formula? So you look at the length of the entire interval, which is b minus a. So because we want them to be a regular partition, so they all have the same length. So delta x is going to be xi minus 1, and you compute it by doing b minus a over n. So look at the entire length, and then divide by the number of intervals that you have. We okay so far? So we have this. Then the definite integral of f from a to b, and the way we write this down is like this: integral from a to b of f of x dx. Exactly the same notation that we had before. The only difference is that now we need to put a pair of numbers here, a and b, and this is called the lower limit, and this is called the upper limit. And this is to talk about what interval we are integrating, okay? Over what region we are integrating. And how do we define this? So it's defined to be, remember, this is a limit. This is the limit as n approaches infinity, the sum from 1 to n. Now, I'm going to say here f of ci times delta x. Let me explain what this ci is. Where delta x is, as usual, b minus a over n. And ci, you know, when we did the example, our ci was the right endpoint of the interval, okay? But as I told you, you could take the left endpoint. In fact, you can take whatever point you want in here. Because what's going to happen? We're taking the limit as n approaches infinity, right? What happens when n approaches infinity? What's delta x? It approaches 0. So those intervals, they're going to be very, very, very tiny. So any point that you pick in between, it doesn't matter. They will all collapse into one point. Do you understand this? Those little intervals, if you want to fit in infinitely many rectangles here, this is, it approaches 0. It's very small. So no matter what point you pick in here inside this interval, they will all collapse together. So it doesn't really matter in the limit. Okay? So xi is just some point inside the I interval. So for example, think of xi of ci to be something in here. Anyways, when that interval gets small, they all collide with each other. In particular, you could take it to be xi or xi minus 1 or whatever you want, as long as it is in the middle. We typically use the left or the right endpoint because those are easy to come up with a formula, as you saw. Okay, like the right endpoint was very easy to come up with a formula. If you want a formula for the midpoint, you can find it, but then you need to work a little bit harder, right? You need to take average and all of that business. All right, so that's the definition, and then A and B are called the lower and upper limits of integration respectively, and the function f, we refer to it as the integrand, okay? All right, so again, this is just me summarizing what we just did before. Now, you can do this process for any function as long as the function is continuous, okay? The function could be positive, the function could be negative. You can play this game. Now, in the case that the function is positive, meaning that on the interval AB, the graph of the function is above the x-axis, when you play this game, you are actually calculating an area, okay? Now, if your function is negative, what's going to happen is you can think of it as an area, but you're going to end up with a negative number because these heights, if your function is negative, what's going to happen to these heights? They're going to be negative numbers. You're going to obtain a negative number as a result. So it's not really an area, okay? What happens is that what you obtain when you do this process is what we call the signed or net area on the graph, okay? So understand that it could be positive or negative, okay? If it's negative, it means the function was under the x-axis. If it's positive, it's because it was above the x-axis, okay? All right, so that's a theorem that you can use this to compute area, but understand that it could come up positive or negative depending on the position of the function. So if you have a continuous function on the closed interval AB, and let A be the net signed area between the graph of f and the interval AB, then this net signed area can be computed by calculating this definite interval. I repeat, when f is strictly positive, then what you do is an honest area, okay? But if the function changes sign, then, when it's negative, you get a negative number. When it's positive, you get a positive number, then the things can subtract each other. In the homework, you have seen this already. You started doing the homework. There are some examples. That on an interval, the function becomes negative, then positive. So this area will be a negative number. Area will be a negative number. Then the top will be a positive number. When you add, they will subtract, actually. Okay, that's what we call net sign area. So I guess I should say here, remark, if the function is greater than 0 on the entire interval, then A above is the area under this graph on the interval AB. Okay? But if the function starts changing signs, then you are no longer calculating area. Understand this? Okay? It's just a net sign area. All right. So the point is, this remark is very important. If you have an integral like this that you need to solve, you don't want to go through the entire process that we just did. Why? Because sometimes the function here is easy enough that its graph resembles a geometric shape. And then if you know that we're calculating area, just look at the geometric shape, find the area, and you're done. Okay? So let's do some examples like that. In other words, let's use what we know from geometry to calculate some basic intervals, some basic definite intervals. Okay, this one is not from geometry, but this one is our first example because we already calculated this the hard way, right? What was the answer here?
22/3.
This is 22/3. And this is just from before. Why? Because we can recognize that since this is positive, here what I'm asking you is what's the area under the graph of this function from 0 to 2, right? Since this function is positive, really the question is, this represents just the area under the function f of x, which is negative x squared plus 5, from 0 to 2. And that was exactly what we computed before. Yes? All right. Once we talk about fundamental theorem of calculus, we are going to go back and do this using that, and you will see how nice we do it in just one little line. Okay? But now, let us keep on using this idea. So, evaluate the definite interval by sketching the region and finding the area with an appropriate formula from geometry. So, what I mean is, what region do you need to sketch? Well, there is a function that you are integrating. That function has a graph. And we are integrating the area under the graph from 1 to 4 in this case. So, I sketch the picture. And maybe you can recognize something easy. For example, this is the function y equals 2. How does this function look like?
A horizontal line.
So as a horizontal line, and then I'm interested from 1 to 4, right? This is the function, y equals 2. Everybody okay with this? Now we want to compute the area under this graph from 1 to 4. So, and it's bounded by the function and the x-axis. In other words, we want to compute this area. What shape is this?
Rectangle.
It's a rectangle. We want to calculate this. Well, this is a rectangle. Do you know the formula for the area of a rectangle? It's base times height or length times width, however you want to call it. So in this case, what's the length? So it would be 3. And what's the and what is the width? 2. So what's the answer? 6. Do you understand this? Length and width. So you recognize the rectangle, okay? The length is 3, 4 minus 1, and the width is 2. You're good. All right. The next one, again, the sketch. Let's see, what do we have here? That's a line, right? And the y-intercept is 2, and the x-intercept is -2. I want, okay, so let me just draw the line. And then we see what we want. It does a line, and then what we're interested is from -1 to 2. So here is -1, and then 1 and 2. Let's see, when I plug in -1, what do we get? We get 1, right? And then when we plug in 2, what do we get into the function? Remember, this is the line x plus 2. We get 4. This is 2,4. So this portion, and is the region under the graph of the function from -1 to 2. So really, we're talking about this right here. Do you understand this? Okay, now let's look at it. What shape is this?
Trapezoid.
This is a trapezoid. And you use the formula for the trapezoid. If you don't remember the area of the trapezoid, well, problem solving. Split it. You can draw a horizontal line here, and you can split this as a triangle, right triangle, and then a little rectangle in the bottom, and then add the 2 areas. Do you understand this? But we have a formula for the trapezoid, so I'm going to use the formula for the trapezoid. So this right here is a trapezoid. We want to find the area. And remember, the area of the trapezoid is trapezoids that have 2 bases. Those are the parallel lines. So this little line is one base, and this one is another base. Okay? So the area is average of the bases times the height. In this case, the height is the side that's perpendicular to the bases. So it will be the portion of the x-axis is perpendicular to the 2 bases. Okay, so let's compute this. Put the equation down here. Okay, so what's the first base? How much is it? 1. What's the second base? 4. And what's the height? 3. Everyone understand this? The height is this length right here. There is 3 units from -1 to 2. Yes? Okay. Compute. So what is this? 5 over 2, so that's 15 over 2. Questions? Let's just computing area. That's all we're doing. And why can we just compute the area? Well, because we realize that this is above the x-axis, and so on. Okay? And we recognize a nice little shape. Are you okay with this? By the way, notice that whenever you have a constant function, that's going to happen. You're going to have a rectangle. Yes? Whenever you have a line, this is going to happen. You either get a triangle or a trapezoid, depending, because it could be, from here to here, and then you have a triangle, right? Or if it's not, from the intercept, then in general, you will have a trapezoid in general, but we have formula for that. So you can deal with lines. That's the point. Now, here is something that with the techniques that we're going to learn in this course, you're not going to be able to solve this unless you use this approach. In Calc 2, there will be a whole section that you're going to learn that's called trigonometric substitution. And with that technique, that's how you solve this interrupt algebraically. But now we can answer this question because we understand. Because if you can grab this, you can recognize this as an area, and it turns out this is a very easy check, and you can find the area. Okay? But if you want to do it algebraically without relying on the geometric content, you need more advanced tools. But we have the knowledge to answer this question. Let's see. The question is, what is this? We already have talked about this at some point, but for example, if you don't understand what is this graph, I mean, you can graph this now. Okay? You know how to graph any function. But we don't have to go through the whole thing about critical numbers, increasing, decreasing, and all of that. Because if we call this y, right, what is this? We can square both sides, bring the x over, and we get this equation. At this point, something should ring the bell. What does this look like? What does this remind you of?
Circle.
What circle?
Positive 7 circle with radius 3.
So, well, let's talk about this equation. So, what circle is this? Center at the origin.
Radius 3.
And radius 3. Yes? So this right here is a circle. So this is a circle. And what circle are we talking about? It's a circle with center at the origin and radius 3. So 3, 3, negative 3, negative 3. Let me say center 0, 0, and radius 3. So we're talking about this circle. Okay. Now, of course, this is not a function. Now, the one on top is a function. Now, if you backtrack this equation, yes, you can get to the middle line, no problem. But then to go from the middle line to the first one, what do you need to do? You need to take square root. Let's put plus or minus in here. Yes. So that means that the circle is really a combination of two functions. The upper half of the circle, that's one function, and the lower half of the circle, that's another function. The circle itself is not a function. It doesn't pass a vertical line test. The equation of the upper half is the positive version of that radical, and the equation of the lower half is the negative version of that radical. Yes? If you were to do this backwards, you have to do plus or minus. Okay, so we have the upper half. That's what we have. So this is the upper half of a circle, right? And then what is the way of doing? We're doing from 0 to 3. Now here the limits are important. If I would have said from 1 to 3, then you cannot do it like this, because here is nice because it's from 0 to 3, so that means that we have exactly what? What is this? What is this? That's a pizza. What part of the pizza is this? A quarter, right? So if you know the area of the full circle, just divide it by 4 and you're done. Now, if I would have said from 1 to 3, you no longer know exactly what piece of the pizza you have, so you will need calculus 2 for this. But here, from 0 to 3 is easy. It's a quarter of the full thing. Also, I could have said from negative 3 to 3. What would be the answer if it's from negative 3 to 3? Half of the pizza. In this case, half of the circle. Does that make sense? So there are some strategic points here that allow us to do this easy. And then, of course, at this point, I have to give you the easy one. Anyways, the point is, that the answer here is a quarter of the area of the circle. Yes? And what's the area of a circle? Pi r squared. So this is pi r squared divided by 4 because it's a quarter. And what's r in this case? 3. So what's the answer? 9 pi over 4. Questions? Again, if it would have been from -3 to 3, then the answer would be half of the area of the circle. So it would be 9 pi over 2. Do you understand this? Because the radius is 3. So pi r squared divided by 2. So the point here is that you cannot forget that you're computing area. When the function is positive, you're really computing area. So if you manage to see what geometric figure you have, when you graph the function, then you can get away and do it that way. Okay, just keep that in mind. All right. And then let's take a look at this one, just to see that, it's not always area per se, but the net area. That's what happens in this example. So let's see. Let's look at the integral. So it's from 0 to 2, but let's draw this line. So this is -1, and then 1. Those are the intercepts. Okay, so this is my line, y equals x minus 1, and then we're interested from 0 to 2. Right? This is the point. No, wait. So this is supposed to be 2 here. It's just the 1, I'm not doing it symmetric. Anyway, that's fine. So because when you plug in 2, then we get 1. So this is the portion of the function from 0 to 2. So from starting at x equals 0 all the way up to x equals 2. So in other words, we have, okay, so I want to be, let me be a little bit more honest to myself because that looks strange. So 1 and then 2. Okay. Now it's better. Okay, so now if you look at this, then the integral from 0 to 2, if you look at it, the area between the graph of the function and the x-axis is, we first have this piece here, right? A little triangle, and then we have this piece over here, which is another little triangle. Does everybody see that? So that's the area on between the graph of the function and the x-axis. So in this case, the function happens to be negative. From 0 to 1 is negative. So from 0 to 1 is going to be under the x-axis. So we're talking about this region right here, this triangle. And then from 1 to 2 is above the x-axis. So it's this triangle over here, right? So you can call this A1, A2. So you can call this one A1. You can call this one A2. And now, this is going to be, the thing is that when you compute A1 and A2, first of all, there are some things that you can understand. This is going to come out to be a negative number because it's a sign area. And this one will come out to be positive. But if you look at it this closely, these are going to be, these two triangles are the same. They are equal to each other. So the answer here, we're expecting it to be 0. Okay? But, I mean, we're going to actually compute it, but understand that A1 is going to come out negative and A2 is going to come out positive. Why? Because when you do this, you're dealing with signed area. Meaning, if something is under the x-axis, you have to recognize it as a negative number. If something is above the x-axis, that area, that portion, that region, the area, you need to recognize it as a positive number. Okay? In the homework, you have a lot of problems, which is just a picture, and you just need to add or subtract numbers, and that's how you do it. If the region is under the x, it's negative. If it's above the x, it's positive. Okay? All right. So now, what is A1? How do we compute A1? That's a triangle, right? So it's a right triangle, so it's base times height divided by 2. In this case, one leg is the base, the other leg is the height. So this is 1 and this is 1. So that's 1 times 1 over 2. And then the other triangle is the same thing, but positive. So we get negative a half plus positive a half. So we have 0. Okay? So, if you want to compute total area, what we need to do is actually we need to take the absolute value of the function. Why? Because total area, you want to make this positive, so you just flip this picture over. Okay? This portion, you flip it over. So, I guess, let me say here, remark. If you want total area, then that will be the integral from a to b of the absolute value of f. Okay? So if the function is already positive, then total area is just the area, because the absolute value is not doing anything. But if the function is negative, what you're doing is you're forcing the graph to go up above the x-axis, so that you are actually computing area. Okay? But in this case, this kind of stuff could happen, that things cancel each other. Okay? That's why we call it the net sine area. Okay. Any questions about using just geometry to answer this simple example? By the way, these are very simple examples, okay? We don't want to do this type of example. We want to do all the stuff. It's just that when the functions get more complicated, then all of a sudden this doesn't work. Like, it's not even complicated, but this little approach does not work for negative x squared plus 5. You could have this is a change that you immediately don't recognize. Like, you don't have a formula for that. Okay? So we need to know all the techniques, which I'm about to explain. Are you okay with this? Now, before I go there, I have been using some properties implicitly. Like, for example, here, I told you, okay, this integral, actually, we can split it as a sum of two sine areas, right? A1 and A2. Now, how do we compute A1? You can think of A1 as the integral from 0 to 1 of the function. So notice that A1, so note, we said that this was negative A1 plus A2. But A1, or negative A1, can be understood as the integral from 0 to 1 of a function. And then A2 can be understood as the integral from 1 to 2 of the function. If you take a closer look at what we just did, basically what just happened, the original integral is an integral from 0 to 2, and 1 happens to be a point in the middle, right? A point somewhere between 0 and 2. And basically what we did was, we used that point to split these as two integrals, okay? So if you want to do from 0 to 2, you could do it first from 0 to 1, and then from 1 to 2, and add the results, okay? This is called an additivity property, and this is helpful when you're dealing with absolute values, for example. So like this, there are many other properties, so I'm just going to summarize those properties, okay? So these are properties of definite integrals. Again, we can just understand these properties based on these basic notions that we have right now. So suppose that you have a function f that's defined at a point A. So what happens when the limits are the same? When the lower and the upper limit are the same? What do you think happens? What would this be?
0.
Regardless of the function. Why?
There's not a space between the two numbers.
Very good. It's just a point. This graph is just a point. And remember, here we're calculating area under the graph. But if you have a point, what's the area under a point? 0. There is no area. There is no width. There is no rectangle that you can put in there. You understand this? Your delta x, if you want, is 0. Okay? So good. So when the lower and the upper limit are the same, I don't care how complicated this function may look like, this is it. Okay? So you can have here a crazy formula. If the lower and upper limit are the same, the answer is 0. Move on with your life. Do you understand what I'm saying? Because again, if you think about it graphically, this is just a point. Here is A. Here is f of A. That's just a point. There's no area under this point. And if it's below the x-axis, then it will be -0, which is still 0. Okay. All right. So another property is the fact that this is when you're dealing with a definite integral, you can play with the limits of integration and you can switch them as you please. Okay. Of course, there is a price that you need to pay. So suppose you have a function that's continuous on AB, meaning A is less than B. But it turns out that your limits are the other way around, from B to A. For example, instead of being from 1 to 2, let's say that it says from 2 to 1. That's weird. We're supposed to have a small number here and the big number in the top. Okay? You can switch the limits, but you need to put a minus in front of the integral. Okay? So that's one little rule. And basically that's because if you think about the definition, when A is less than B, remember that delta x is B minus A. That's a positive quantity, right? If you switch the limit, what do you have instead of B minus A? You have A minus B, right? But that's a minus. So B minus A, you can switch them, but if you switch them, you have to put a negative. So when you do this, then this negative is going to carry to the outside of the integral. Okay? So that's the reason why. I mean, if you want to justify this property. The point is that you can fix the limit. You can put them back the way they're supposed to be, but you need to pay a price. What? Put a minus in front. So you're allowed to switch the limits of integration if you want to, but you need to put a minus in front. That's what this property is telling. Okay? And the reason is because the delta x changes sign. So for example, in this problem, what's the first integral?
0.
This is just 0. I mean, I don't even care what to do with the sine function from pi to pi. That's all I need. Say limits, that's just 0. The next one, well, this is the same thing as minus the integral from 0 to 3 of x plus 2, right? And we did this one. How much was this? We did this one from before. What was the integral from 0 to 3?
15/2.
So,
Or -1/2.
we didn't do that one. Okay, so then I guess, okay, let me do the picture then. I should have. That's okay. So now if you want to do this one, let's do it quickly. I mean, once we know more, then we can do it more quicker, but that's fine. So let's see, x plus 2, so here is 2, here is -2, right? So it's something like this. Now we need to go the way up to 3. What is this point? That's 3,5. So we're basically calculating this area. Right? So what is this? So this is 5 times 5 divided by 2. But remember, it's a negative. Actually, no. It's this. From 0 to 3. So it's this. Okay. So it's a trapezoid. So it's going to be 2 plus 5 over 2 times the base, which is 3. And then with a negative. So the answer is going to be, so what is this? 721, so -21. Okay. All right. So we have that. Then the other one is the additivity property, which is the one that we used before. That if you want to integrate the integral from A to B, sometimes it's nice to split the integral. Again, that's useful if you have an absolute value. You want to get rid of it because you cannot use fundamental theorem of calculus with an absolute value. You want to use it, you need to get rid of it. To do that, you need to know when the function is positive, when it's negative. And if it changes sign in your interval, then you have to split it into different pieces in which it's always positive, then always negative, and always positive, always negative. So you can remove that absolute value. Okay? So that property is very helpful. And the picture that comes together with this is pretty straightforward. Let's say that this is your function y equal f of x from A to B. The integral from A to B of the function f is basically the area under the graph. So all we're saying is, okay, look, you can just pick a point between A and B, and then it's okay. Instead of doing the whole thing at once, you can compute this area. You can compute this one, and then what can we do to get the area of the whole thing? We just add them, right? So if this is your A1 and if this is your A2, compute A1, A2, and then you add them. Now, what's A1? That's the integral from A to C of f of x plus the integral from C to B of f of x. Okay? So the little clue here is that you can do always this splitting, and also this is nice. You can look at it from right to left. When you have a sum of two integrals and the upper limit here matches the lower limit, you can condense them as one integral. Okay? And this technique is used a lot when we are doing some computations. So whenever the upper limit matches the lower limit of another integral, you can write this as a single integral. Okay, so we have that. You okay with this? For example, that can be used here, as I mentioned. So if you want to do, well, here you could do if you wanted to, in this case, it's something that we can graph, so let's just graph it. So this is the absolute value. Let me put it here. From -1 to 1, right? You know this is 1. And then what we're trying to compute is this area together with this area. Now, if you do it all at once, it's not clear what shape is this. But now, if we split it into two little integrals, then we see this is a triangle, this is also a triangle, right? So you can think of this as the integral from -1 to 0 of the absolute value function plus the integral from 0 to 1 of the absolute value function. Now, the first one is this A1, the second one is this A2. So what is this? So that's 1 times 1 divided by 2. So it's going to be 1/2 plus 1/2. So the answer is 1. Again, numbers are positive because everything is happening above the x-axis. Okay? If you wanted to, later, if you want, we can come back to this using Fundamental Theorem of Calculus to see how you can get rid of that sort of value algebraically. But basically, the point is that 0 is that transition point in which it changes from negative to positive, the function y equal x. Okay? So to the left of 0, you have to put a minus x. To the right of 0, you have to put a positive x. Okay. So as that property, and then here are some other things. That, for example, because an integral, a definite integral is just a limit. Okay. The same way that you can take constants out of a limit, you can take constants out of a definite integral, just like what we do with indefinite integrals. So this is just k times the integral of f of x. Okay, from A to B. And then similarly, because the limit of the sum is the sum of the limits, the limit of a difference is the difference of the limits, then if you have a definite integral of a sum of two functions, you can split this as the sum of two integrals. Okay, so find the area of f, then find the area of g, and then you add, but also you subtract. Now, let me emphasize on the subtraction part. Let me show you the picture for that one because you're going to be doing this in Calc 2 as well. And also here, this is one of the applications we're going to use. You can use this now to find actually the area of any region in the plane as long as you know the equations for the curve that bound this region. For example, imagine that you have your function f over here, and your function g happens to be under f, less than f from A to B. Okay? What happens before A or after B, I don't care. But between A and B, let's say that we have this condition that f is above g, and let's say that what you want actually is the area in between, the area of the region bounded by these two functions from A to B. So we want to calculate this area. So naturally, how would you compute this geometrically? You can find the whole thing for f, then the whole thing for g, and you subtract, right? Because you can do the big thing, subtract this empty part that we don't care about, and you're going to get this, right? So to find the area between two curves, what you can do is you find the area of the top curve. So let me first write in words. So the area is going to be the area of the top minus the area of the bottom. Do you understand this? In other words, the area of F, which is the top curve, minus the area of the bottom. Okay? Now, let's look at it from another perspective. Let's put it as one little integral. Okay? Which is, doing this property backwards. And basically what we're saying is that if you want to find the area between two curves, all you have to do is figure out which one is the top, which one is the bottom, and so you just integrate the difference of the 2 points. Top minus bottom. Okay? So, it's important. And if you have a picture like this, if we have time today, we'll do an example like that. Imagine that you have a picture like this. Okay? So let's say that this is your function f, and this is your function g. And let's say that this is a, this happens at x equals b, and this happens at x equals c. Okay? And of course, in practice, how do you find information? Either it's given to you already, or if I give you f and g, then you set them equal to each other and solve the equation. You find the points of intersection, that will tell you, how many solutions you have. Those will be the points in which they cross. Now, let's say that I want you to find the area bounded by the graph of f and g. In other words, anything in the plane that's bounded by these two graphs. So you should understand that I'm talking about this, but also I'm talking about this. Yes, as the area bounded by f and g, between f and g. Now, can we compute this in one shot? Well, no, because notice that the yellow area, the function f is on top and the function g is in the bottom. And the blue area is the opposite. G is on top and f is in the bottom. So in this case, the area bounded by f and g, how would you compute this? Well, you have to split it as two areas. So it's going to be A1 plus A2. And how do we find A1? That's the integral from A to B of top minus bottom, plus what's A2? Integral from B to C of top minus bottom. Is that clear? So remember, how do you find area between two functions? Top minus the bottom. For example, what we have been doing so far, you can think of this as top minus bottom. It's just that the bottom function is always the x-axis when you just do the integral of x. Okay. But if we can introduce more functions, and then literally it's top minus bottom, but now you have to know when f is on top, when it's in the bottom. And you either graph or you solve the equations and the inequalities. Okay. All right, so just keep that in mind. And then number 5 is the preservation of inequality, meaning, the first one should be clear. If a function is already above the x-axis, what are you expecting when you take an integral? What should be a definite integral?
Positive.
It will also be, a non-negative number. It could be 0 or positive, right? So basically, if your function is already positive, your integral will be positive. And also the fact that it basically respects inequality. So if f is less than g, that means it's below g. The area under f is going to be less than the area under g, right? So if f is less than or equal than g, then the integral of f is less than or equal than the integral of g. Okay, on that entire integral. So just think about it as areas. Just look at this picture. G is less than f, so the area under G is less than the area under f. Okay? So if you do integral, the inequality is preserved. Is that okay? Okay, so those are basic properties. But now, and we were able to understand those just from the definition. Okay? But now, let's get a little bit more technical in the sense, okay, let's now talk about how do we compute this in an efficient way. Okay? Because doing this limit and approximation is really not a good idea at this point. So then we have a theorem. That's a very important theorem. It's called the Fundamental Theorem of Calculus. And as I explained last time, or as I mentioned last time, I didn't really explain, is that this is a theorem that connects the two pieces of calculus. We have differential calculus on one side, derivative, limits, and all that business. And then we have integral calculus on the other side, which has to do with this computation of area. Here is the notion of tangent line, that's differential calculus, and the notion of area, that's integral calculus. And then this theorem links these two words together, okay? And basically it says the following. By the way, it has two parts, okay? The one that's most commonly used, part one, but I'm gonna just mention part two. Okay, so part one says the following. Suppose that you have a continuous function on a closed interval, okay? This is just so that we can talk about area, okay? And let f be an antiderivative. What does this mean? What does that mean?
Big F prime is equal to.
Exactly. This is a function whose derivative is little f. Right? That's what that means. Okay, so suppose that you have a continuous function and that you know an antiderivative of this function. Now, the first statement is, if you want to find the area under the graph of this function, or if you want to compute the definite integral, you can do this as follows. You have your limit definition, rectangle, blah, 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 but actually there's an easy way. Just take your antiderivative, evaluate it at the upper limit, evaluate it at the lower limit, and subtract the two numbers. Okay? Why this works, that's a whole different story. Unfortunately, I don't have the time to explain it. But if you want, if you are interested, then we can talk about it later. But it's actually a very strong theorem because it allows you to do a problem that took us an entire page to do it in one line. Okay, it's a very strong statement. All you have to do is find an antiderivative. So you do the indefinite integral. We were playing the game last time. Find an antiderivative and then plug in your limits of integration and subtract it. Okay, and that magically gives you the area. By the way, we have a notation for this. That comes in handy if you have started doing problems, then you have been using this notation. The way that we write this is, we have our function, whatever the antiderivative is, and we put a line, and we put the a and the b here. This just means, when you see this just means take whatever is in here, evaluate it at b, and then minus this, evaluate it at a. Okay? That's just a handy notation that comes when we're solving it. Okay, so we're gonna do, I'm gonna mention part two, but let's do this one. For example, this was the very first one that we did, okay? Now let's do it using fundamental theorem of calculus. So what do we need to do? Find an antiderivative. So, antiderivative. Remember, I just need a function whose derivative is that. So in other words, to find my f, you can do it by just doing the indefinite integral. And we can do that easily, right? Just a power rule. So what is this? Negative x cubed over 3 plus 5x plus c. But then I just need one antiderivative. So this is what I'm going to take as my f of x. You okay with this? So according to the fundamental theorem of calculus, this is going to be my antiderivative. And then I'm going to evaluate it from 0 to 2. So if you plug in 2, what do we get? We get negative a over 3 plus 5 minus, and if you plug in 0, what do we get? 0 plus 5. So what is this?
Yeah, 5x.
5x. Yeah, okay. 5x here, so that would be 10. And then here, that would be 0. Okay, good. What about, we're going to find out if we're not going to get the same number. Okay, good. So you plug in 2, you get negative a over 3 plus 10. You plug in 0, you get 0 plus 0. Right? And when you subtract, we get negative a over 3 plus 10. And if you remember, this was exactly what our limit gave us, right? So when you combine, that's 22 over 3, as we computed at the beginning today. And the point is that you can now do this essentially in one line, okay? Instead of having to do all of that computation from before. So to now find a definite integral boils down to just being able to find antiderivatives. All the techniques that we talked about last time, substitution and all of that business, now you can bring it into the mix, find your antiderivative, and then once you have it, plug in your limits of integration, and you're good to go. But don't forget that you are computing an area, okay? Because you need to know what you're doing. You okay with this? Yes.
Is it sometimes easier to just draw the picture or not? Like, if you know how to just go ahead and do it.
No. I mean, You need to know this notion of area, because if I give you the one with the circle, the only way for you to do it is drawing the picture, because you don't know the techniques to attack that integral by doing this. How do you find an antiderivative of the square root of 3 minus x squared? Good luck trying to do that. Okay, so in Cal 2 you will learn how to do that. There's something called trigonometric substitution that will allow you to deal with this. Okay, so that's why it's good to know this approach of area. But in practice, you know, the one I'm going to give you is stuff that you can compute. So you just compute it. Okay. In Cal 2 you will spend a lot of time learning techniques on how to find antiderivatives, so you can do this kind of things. Okay, without having to rely on the graphing part. All right, are we okay with this? Okay, so I guess let me do some basic examples. I guess let me say a few words about part 2. So part 2, basically what it says is the following. Now that we understand that area, that this integral talks about area, there is a function that we can define. It's going to be a little bit weird, but let me just draw a picture here. Imagine that this is your function f, little f, and then here is a. Okay, and then there is a function that I can make by doing the following. Okay, I have this graph, and then I want a function that keeps track of all possible areas under the graph of this function. In other words, if x is in here, the output of my function at this x is going to be the following. I compute this, and whatever this area is, that's the output of the function. Okay, if, for example, if my x is down here, then I do this, and then the area from A to B, that will be the output of my function, and so on and so forth. So remember, the function is give me an input, and then I give you an output. I'm calling that function capital T. Okay? So look at the setup. The reason why I'm using T here is because I'm using x for my input. So here is where the input of the function goes. Okay? So this is the input. Input. So if you put a number in here, for example, if this number is bigger than A, then what I'm calculating is this scenario that I'm telling you. It's the area from A to whatever that number is. The answer is going to be a number. So giving an input, you obtain an output. Yes? Nobody can stop you from doing this. Now, understand that I can put numbers in here. You just flip it and then you put minus and all of that pieces with the properties. So every time that you define a function like this is a well-defined function. The claim is that this is actually a nice function. It's continuous. It's differentiable. And moreover, the derivative of this function happens to be exactly what we have here. Okay? That's the second part of Fundamental Theorem of Calculus. So when you define a function like this, the derivative is just the stuff that you are integrating. Okay? And it kind of reminds you of this relationship between derivative and integration, right? So we're basically saying that g is an antiderivative of little f. That's what we're saying. If you have a function and you play this game, what you're doing is you're making an antiderivative. That's the point. So if you have a function and you don't know how to come up with a formula for the antiderivative, you can just form this integral. As long as the function is continuous, that will be an antiderivative. Now, of course, this is probably not too helpful because you want an actual formula to deal with. Okay? But that's an antiderivative. That's what part 2 is saying. Again, this is just for your information. We're not going to be doing much with this. Okay? There could be 1 or 2 problems in the homework that deal with this, but then that's it. All right, so I really want you to understand how to use part 1. So let's practice that a little bit more. So now if you want to compute this, again, this is something that we already did. What was the answer for this? It was 0, right? It was the one that we had the 2 triangles and they cancel each other, okay? Well, let's see, let's compute it. What do we need to do? Find an antiderivative. What's an antiderivative of x minus 1?
X squared over
X squared over 2 minus x. And then evaluate it from 0 to 2. Do you understand this? All right, let's plug in. You plug in 2, what do we get? So we get 4 over 2 minus 2, then minus, then plug in 0. That's 0 minus 0. Yes? So what's the answer here? 0. As expected. So for example, this one we could have done it with the algebra, with the area approach. And now this one, forget about doing it with the area. Because if you draw e to the x, what's the change? I don't know, it's e to the x, but we don't have a formula for that, okay? And now, Fundamental Theorem of Calculus comes to the rescue. We just need an antiderivative. What's an antiderivative for this function? What is it?
5ex.
5e to the x, right? So you can take the 5 out and then antiderivative of e to the x, just e to the x, and plug in from 0 to ln of 3. So we have 5 times, now I'm just going to left the 5 outside, that's e to the ln of 3 minus e to the 0. What's e to the ln of 3? What's e to the ln of 3? That's 3. So that will be 3 minus 1, right? Remember, e to the 0 is equal to 1. So the answer is 10. Questions? Do you understand this? As long as you can find the antiderivative, you're good to go. All you have to do now is plug in the limits. Let's do a more interesting one. So again, we want to do this. Remember, the function has to be continuous, so even though typically we ignore this kind of stuff, you have to be mindful of this. If I do this, if it would have been from -1 to 4, you cannot use fundamental theorem of calculus. Because this function is not continuous in that interval. This function has a problem at 0. In fact, it has a problem with all negative numbers, right? So let me not even do that. If I would have been from 0 to 4, this function is not continuous at 0. It's not continuous in the interval, so fundamental theorem of calculus is not applied. This is what we call an improper interval. You're going to study this in Cal 2. Okay? You're going to study this in Cal 2. So you always, take a glance at the interval of integration, make sure that your function is okay in that interval. In this case, we're fine. From 1 to 4, there's no problem with this function. So we need an antiderivative because that may be a little bit of more work. So let's do it here on the side. Let's find the indefinite integral first. Okay, so how do we do this? At this point, you should be masters of this already. So what do we do? So x to the -1/2 minus 3x to the 1/2, and then power rule, right? So that would be x to the 1/2 over 1/2 minus 3x to the 3/2 over 3/2. So 3's cancel out. So we get 2 square root of x minus 2x to the 3/2 plus c. Now here we don't really need the plus c, right? Because we just want one antiderivative. So just take it without the plus c. So this would be my antiderivative. Okay. So now we go and we write it down. So that's 2 square root of x minus 2x to the 3/2, and then plug in from 1 to 4. Okay? So let's see. When you evaluate at 4, what do we get? 2 square root of 4 minus 2 times 4 to the 3/2 minus evaluated at 1. Okay, when it's at 1 is just, right? So that's 2 minus 2. Everybody okay with this? Okay, so that's a 0. Now what is this? So 2 times 2, so square root of 4 is 2, so that's a 4. And then when you do 4 to the 3/2, you do the square root first. You can do the square root first, which is a 2, and then you cube it. It's an 8. And times 2, that's a 16. So I give you 4 minus 16, and then you get -12. Okay, remember, it's okay to obtain negative numbers. That just means that, remember, this is the sign, the net sign area. Okay? Questions about this so far? No? Okay, so let me show you. Let's do something more, a little bit more interesting, probably slightly more interesting, in which we need to do some substitution. Okay? So there is a substitution theorem. There is a version of the fundamental theorem of calculus when you use substitution. Okay? So technically, you don't really need to write a version. So technically, as long as you find an antiderivative and then you use all the substitution there, you're good to go. But then you have to make sure that you find your antiderivative in terms of x. The thing is that when you do a substitution, when you go back to the linear variable, sometimes you have a very nice little integral, but when you replace back your u, you get a big expression. And then having to plug in your a and your b in there is going to be a mess, and you can make algebra mistakes. Okay? So to avoid that, it's good practice that when you want to use substitution in a definite integral, okay, there's really no reason to go back to x anymore. It's just that when you make a substitution, change the limits accordingly. Okay, so let me show you what I mean. So, fundamental theorem of calculus with substitution basically says, suppose that you want to integrate the function from a to b. Right. So the integral from a to b, now, as you know, substitution in general, it deals with, it's a composition and the g prime showing up and so on, right? So this is the general form that it looks like. So if you want to compute an integral using substitution, you can do the following. So you can let u be equal to g of x, right? Then, as you know, du is going to be g prime dx, right? This is what I talked about on Friday. Then this will become the integral of f of u du. But now the point here is that this no longer will be an integral from a to b, because now these bounds, these limits a and b are with respect to the variable x. We are changing from x to a new variable, namely u, right? Well, what happens when x is a? What's u equal to? G of a, right? I mean, u is g of x, so when x is equal to a, u is g of a. And what happens when x is b? U is g of b. So all you have to do is, instead of a, you put here g of a, and instead of b, you put here g of b. So you change your limits accordingly, using the substitution, and then, because the answer here will be a number, it doesn't matter if your variable was x or u, you never have to go back to x. Remember, when you use substitution, you always have to go back to x, because you were doing an indefinite integral. But if you're doing a definite integral, the answer is a number. It doesn't matter what the variable was, as long as you change the limit. If you don't change the limit, that's fine. You find your antiderivative, but then you need to go back to x to plug in the original a and b. But you make find yourself with a mess in here, like something very, very big, very huge, and then you have to plug it in there. Okay, that's not advisable. So I will be changing limits. Okay. All right. Are you okay with this? Let me give you an example. Let's see. Let's do an interesting one. Let's do the integral from 0 to 1 of x times the square root of 1 minus x squared dx. Notice the domain here is from -1 to 1, so we're good. Okay. All right. So we want to do this integral. Hopefully you realize that substitution is in order. And what should be a substitution here? What's the substitution? U equals 1 minus x squared. So we let u equals 1 minus x squared. So what's du?
2x
Negative 2x dx, right? And then remember, because we only have x dx in here, that's not a problem. We just divide by the -2, right? So now we make a substitution. So this becomes the square root of u, and then x dx becomes du over -2, right? But now I'm going to change my limits as well. So let's see, we need to plug in 0 and 1 into a substitution to get the new limits. So when x is 0, what is u equal to? 1. And when x is 1, what's u equal to? 0. So now my new limits are from 1 to 0. Do you understand this? And we do it by just, plugging into a substitution. All right? Now, I'm going to take out -1/2 from 1 to 0 of u to the 1/2 du. Now, if you don't like this from 1 to 0, I don't like it either, we can fix it. We already have a negative on side. What can we use this negative for? Remember one of the properties. We can flip the limits of integration, but then you need to put a minus. But we already have the minus there, so you can use it to put the limits back. So now the minus is gone, and this becomes from 0 to 1. Okay? And now we integrate. So that's u to the 3/2 over 3/2 from 0 to 1. So it's going to be 1 over 3 times, now when you plug in 1, you get 1, and you plug in 0, you get 0. So the answer is 1/3. Okay. Questions? Did you understand this substitution? You do one more. How about, let's see, something slightly more interesting? If I do anything more, I'm gonna take. Okay. How about this one? Was the integral from 0 to 2 of e to the negative 2x plus 2 sine of x. Let's do this. Okay, so here this is a sum, right? So we can write it as a sum of two integrals if you want, right? So you can think of this as two little integrals from 0 to 2, e to the negative 2x, plus the integral from 0 to 2 of 2 sine. Yes? All right, so how about the first one? What's an antiderivative of e to the negative 2x? Can you think of this? If not, what do? You can use a little substitution. Now, at this point, for this one, you should not use substitution because here, basically, this will be e to a negative 2x, but then you need to divide by negative 2. Why? You have to compensate the chain rule. Remember, you want a function whose derivative is this. And as you know, e to the x is derivative of e to the x. So what's the derivative of this function? E to a negative 2x times negative 2. So if you want to compensate by that, you have to divide. So you cancel the negative 2. Okay? But if you don't see that, then, you make your little substitution. So you can say, oh, let u equals negative 2x, then du is negative 2 dx. So dx is du over negative 2. So then this becomes e to the u du over negative 2, and now I change my limits. So when x is 0, this is 0, but now when x is 2, this is a negative 4. And for the other integral, I can take out my 2, and what's an antiderivative for sine? Negative cosine, be careful. And now we plug in our 0 on it. Okay, so as before, I'm gonna take out 1/2, and if you don't mind, I'll do several steps at once. I take out the 1/2, the negative will flip my limits, yes, from negative 4 to 0, and the antiderivative is e to the u. Because the integral of e to the u is just e to the u. And again, the reason why you see these things switch here is because of the negatives that we had in here. Do you understand this? The negative is the one switching those. Minus 2. Then this is cosine of 2 minus cosine of 0. So what is this? So e to the 0, that's a 1, minus e to a negative 4. And then minus 2 times cosine of 2 minus 1. So cosine of 0 is 1. And this is, well, whatever it is, okay? That's a number. Because I just made up that problem, so that's why it's not so pretty. But it's a number, that's our answer. Okay, any questions? So now hopefully you understand what a definite integral is, okay? Again, I'm not gonna require you to do a limit definition, but I want you to know what it is. But then make sure that you understand how to use Fundamental Theorem of Calculus. Now, 2 examples. If you get stuck in the homework, I'm in my office. I'm going to be there today until 1:30. I'm going to be there tomorrow from 11:30 to 1:30 as well. Okay? So you can come and ask to do more examples, but you basically have everything you need.